guess we'll wait a few more minutes for more people. Has anyone been watching the video lectures?
Just about the real line topology.
And what is defined, properly defined there?
I think open sets and closed sets are nowhere and no attempts.
But just for the real line, not for a general
Yes.
topological space? Okay. So we were not given a new list of problems. We only have 2 problems left from the last list. So maybe it will be useful today to just start with a few general definitions. I don't see why to postpone giving the real definitions. Because the first set of problems was about graphs in the plane or on the torus, for which we didn't even have a definition of open set. So maybe we can go back and try to define things properly. So why don't we just say it first for Euclidean space and then for a general topological space. So this is a generalization of whatever it was you were told for the real line. So an open subset of Rn, and this is in the standard topology. Maybe you can put some weird topology on Rn, but let's just do the standard topology. So let me say it like this. A subset U in Rn is open if for every point in U, there's some open epsilon ball around X that's contained in U. So I look at the epsilon ball around X. That by definition is points X prime, so that the Euclidean distance between them is less than epsilon. And that should be contained in U for sufficiently small epsilon. Okay. So an open set by definition Equivalently, an open set is a union of epsilon balls with various centers. Okay, so that's the definition of a standard open set. And a closed set is a complement of an open. And the basic properties are the following. So first, the empty set and all of our n are open. The empty set, because there's nothing to check. The condition is empty, it's vacuously true. For Rn, there's no point, so you don't need to find an epsilon neighborhood of that point. For Rn is a union of epsilon balls, in fact, of balls of integer radius. Just set everything to be centered at 0 and then let the radius grow and grow, and that will cover Rn. It's an infinite cover, but it's a cover. So it's a union of balls. The arbitrary union of opens is open. Because a union of balls, a union of unions of balls is a union of balls. And this is maybe a little more interesting. Finite intersections of opens are open. So why is that? Suppose I have a finite intersection and I have a point in there. How do I find an epsilon?
You choose the minimum of epsilons for every u. It exists because all of them are positive for you.
Yeah, each of them is open by definition, so each of them contains some epsilon ball. The epsilon depends on I, and you could just take epsilon to be the minimum of the epsilon i's. And then this will be contained in each of the epsilon i's. Because if I keep the center the same and shrink the radius, I get an inclusion of balls. So for each I, it will be in there, and therefore it will be in the intersection of all the ui's. Okay, and these three properties here, this is the definition of an abstract topological space. We say a topological space is a set of points. We call them points. X together with a collection of subsets called open. Satisfying these conditions. So maybe we should name them. Let's call this one 1. And here I should require this to be X, not necessarily Rn. This is condition 2. Union of opens is open, and 3 finite intersections of opens are open. So anytime that's satisfied, you call this a topological space. And all the notions that we've been discussing so far, like closure, limit point, and so on, all make sense in this context. Okay, so that's the general definition. And the way you make precise what we did during the very first seminar, where we were gluing together rectangles along edges. Let me do an example. We were doing this implicitly, but explicitly, if T is the torus obtained as a set, by gluing together opposite edges, so let's draw the picture we had before. So let me draw in the same color those edges which are going to get identified. So the torus as a set is going to be equivalence classes, where corresponding points on the two red edges get identified and corresponding points on the two blue edges get identified. So this is the equivalence classes. This is the rectangle modulo this equivalence relation as a set. And I have to tell you what is an open set. So if I'll call this Q for quotient. When you impose an equivalence relation, it's called taking the quotient. So we say U in here is open if, so this is by definition, its preimage is open. And I suppose I have to tell you also what is open inside the rectangle. So I embed this in R2. And a subset of the rectangle is open if, let's call the rectangle, this is my X, maybe Z. If it's equal to the rectangle intersect and open in R2. So the open subsets of the subspace are just those that arise by restriction from the ambient space. In general, you can do this for any subset of a topological space. You can declare there to be a topology on it whose open sets are intersections with opens in the ambient space. So this is the definition, and you can verify just by the way preimages of surjective maps work. You can verify that this is a topology on the quotient. So it in fact work for any surjective map of sets where the source has a topology. You get a topology on the image. Okay, so I hope that makes things a little more precise. Are there any questions about the definition or examples?
So in our case, a point in equivalent class contains 1 or 2 points in this case. 1 or 2 or 4 points.
Right, so yeah, it depends. So indeed, if I draw, all of these are getting identified, right? So I've drawn it inside there, inside the torus. At the point where the red and blue loops intersect, that green point, the pre-image has 4 points. For any other point on the red loop or on the blue loop, the pre-image is 2 points. And for any point in a white, the pre-image is a single point. So I'm partly just using up time because they didn't give us a new list of problems, but I hope this is helpful. So you could do something similar for the Klein bubble or the Möbius strip. By definition, the open sets would be those whose pre-image is open. Is it worth verifying this fact that if I have a topological space and Y is a surjective map to a set, that I can define a topology on Y? So by definition, the quotient topology on Y a subset is open if its pre-image is open. Is it worth walking through the verification that this is a topology? Or do you want to? What's that?
Can you show me?
Okay. Yeah, so let's try. So what's the first? We have to check that the empty set and all of Y itself are open. So what is the pre-image of the empty set?
Empty set.
Good. Okay, so that's definitely open since X is a topological space. What is the pre-image of Y?
X.
X, which is also open because X is a topological space. Very good. Suppose suppose I have a union of opens. What is the pre-image of a union?
Like union of pre-images of each UI.
Yeah. So that's a fact about maps between sets. You can verify that by checking that elements of one side are contained in elements on the other. Okay, so if each of the UIs is open, then by definition, the pre-images are open. And since X is a topological space, their union is open. Therefore, the pre-image of the union is also open.
Okay.
And finally, same for finite intersections. You could take the pre-image. And you can also check pre-image behaves well with respect to. This. Now, can you give an example? What's an example of an infinite intersection of opens, which is not open?
Like infinite intersection of balls with radius which goes to 0, which goes to small, very small.
Right. All right. So let's do the intersection for all epsilon greater than 0. And then what's the intersection?
Point 0.
The point 0. And the point 0, for instance, in Rn. And that's not open because you can't fit a positive radius ball inside of it. It contains no ball. Okay, so that's why the finiteness condition is important. Okay, the only other general thing we could do is, before doing the last two problems on our list from last time, we could talk about continuous maps between topological spaces and compare them to the usual definition with epsilons and deltas. So let's just recall the usual definition. So suppose I have a map from one Euclidean space to another. And suppose I have a point in here, x, which maps to a point y. Does anyone recall the definition of f being continuous at x? Okay, so what you said is the following, and then we'll translate it into the more classical notation to compare them. So what I think you said is f is continuous at x if for all epsilon greater than 0, there exists a delta greater than 0 such that the image of the delta ball around x is contained in the epsilon ball around y. Yes? Now let's rewrite that in a way that maybe looks more familiar from analysis. This is not usually how it's said in a calculus book, but it's equivalent. So what you would normally say is for all epsilon greater than 0, there exists a delta greater than 0 such that x minus x prime, so maybe I should call this x naught. So if the distance between x and x naught is less than delta, then that implies the distance between f of x naught, which is y naught, sorry, f of x and f of x naught. Is less than epsilon. In other words, if I want to ensure that the image of a point is close to the image of x naught within a given distance epsilon, I can find a distance delta within x naught so that it's ensured. Or very roughly, points nearby to x naught map to points nearby the image of x naught in a controlled way. Okay, so these are equivalent, and let me say it a third way. So the epsilon balls are just among the many, many open sets of Rn, and it's sometimes convenient to not worry about only epsilon balls, but more convenient to think about all open sets. So this is equivalent to instead of all epsilon balls around the image, why not? We could say for all opens containing the image of x naught, there exists an open containing x naught whose image is contained in the neighborhood. It's called, if I have a point and a open containing it, it's called an open neighborhood or just a neighborhood. Some people allow neighborhoods to be something more general. I'm going to require them to actually be open by default. So why is this equivalent to the first thing? Why the epsilon ball version and the any open set version the same?
Well, every open set containing x0 contains a ball around x0.
Mm-hmm. And in fact is, right, so in the latter condition involving u and v, it immediately implies the condition with the, like you said. So I fix v to be the epsilon ball, then I find a u, and inside of that u, I can find a delta ball. Conversely, if I can play this game for epsilon and delta balls, how do I do it for a general v?
Then V contains epsilon ball.
Mm-hmm. I would say V is covered by epsilon balls. Well, okay, fine. Choose an epsilon ball around f of x naught that's contained in V. Very good. And then take U to be the corresponding delta ball. Yes?
Yeah.
Okay. So these are equivalent. And what's convenient about this is that in this last version, I didn't need to mention epsilons and deltas. I just mentioned open sets, and open sets make sense for any topological space. So a general topological space maybe doesn't have a notion of distance that allows you to define an epsilon ball, but it still has a notion of open set, and so I can take this as the definition in general. The definition, a map, let's say, yes. A map f x to y between topological spaces is continuous at x if this condition star is satisfied. So that's the definition of being continuous at the point x, or x naught. And we might be interested in continuity everywhere, and it turns out there are two ways to say it. So I claim the following are equivalent. This is continuous at each point in x. That's one condition. The second condition is for all opens in y, the preimage is open. call this A and this B. So we should verify the equivalence between these two. So suppose A. Suppose F is continuous everywhere. And suppose U in Y is open. So there are two cases. Either U contains nothing in the image, or it contains something in the image. So suppose U contains nothing in the image of F. Then what can you say about the preimage of U?
It's an empty space, which is open.
Right. So if U intersect the image is empty, then the preimage of U is also empty, hence open. Otherwise, suppose I have some point which maps into U. Then what does continuity at X tell us? Right. Right. And that works for any X. So let's call this V sub X. This works for any X that lies in U. Yes? So this whole open set Vx, since it maps into U, that means it lives in the preimage of U. Yes? Every point of V sub X maps into U, so by definition, it's in the preimage of U. And so now how do you explain?
And the preimage of U is a union of all these Vx for all X.
Yeah, that's right. So X such that f of X lands in U. Okay, and therefore it's a union of opens, hence open. Okay, so that's A implies B. And I think B implies A is even easier. But let's write it down.
So we need to prove that for every point in Y, for every open set that contains it, there exists an open set in X. Image of that will be our set in Y. But it's just by definition of.
Well, let's say it carefully. It's not every
our set in Y is open set, so the image of this open set will be the set in Y.
Yes, but let's say it carefully because it's not for every point of Y, because not every point of Y need to be in the image, right? So let's say it like this. For all X, choose a neighborhood. Okay, consider its image. And choose any neighborhood. Then, as you said, its pre-image, that will be, let's call it V. It will contain X because X is in the pre-image of UY. And if I apply F again, that will land in UY. And this is open by continuity. So this is open by hypothesis. So that's what we need. So indeed, that's easy. So these two conditions, A and B, are equivalent, and any map satisfying them is called continuous. So F is continuous, full stop, if A or B, they're equivalent. So maybe I should say, because say A or B, you can verify either, but it's also A and B since they're equivalent. Okay, and we've already seen an example. So first, all of the examples you know from calculus, you proved that they were continuous using epsilons and deltas, and then they're continuous in this sense as well, because those are equivalent for the standard topology on Euclidean space. But we also had this example, for instance, where I took a topological space and it's projected onto some other set, and I give it the quotient topology. And remember how we defined the quotient topology. We said a subset downstairs was open precisely when its pre-image was open. And so by definition of the topology on Y, this quotient map is continuous. So the topology on Y is defined to be, topology on Y is defined to be so that Q is continuous. And in fact, it's more than that. It's the finest topology. It's the greatest possible number of open sets for which Q is continuous. If I tried to add an additional open set into Y that didn't have this property, then this map would no longer be continuous because the preimage would not be open. Okay, so that's a little bit about what is a topological space and what is a continuous map. We have left 2 more problems from the list. Is this list posted anywhere where you can see it? Maybe on this Sirius platform?
I think so.
No? Okay, I'll ask whoever is handling this. I think her name is Galdienko. I'll ask her to put this information somewhere where you can find it.
Sorry, maybe you could prove that this is finest topology indeed.
Okay. So I guess we should formally define comparison topologies, finer and coarser. So given 2 topologies, let's call them tau 1 and tau 2. So topology by definition is a collection of open sets satisfying the axioms for open sets. On a set X, T1 is coarser than T2, and that's the same, or from the other point of view, T2 is finer than tau 1 if every open set of T1 is also an open set of T2. But there might be more open sets in T2. So here's a really stupid example. Stupid example is take any set X, for instance, the set with 2 points, call them 0 and 1. But the following is going to make sense for any set. Then T1 consists of the empty set and the whole space.
Excuse
tau
me.
1. Yes.
T1 is a set of open sets inside.
Yes. So by definition, topology is a collection of subsets called open that satisfy the axioms for a topology.
Okay.
So here's a really stupid topology on a set X. I declare the open sets to be the empty set and X itself. Okay. This is called the discrete topology, indiscrete. And here's another one. Any subset, including 1-point sets. This is called the discrete topology. Everything is open. So which one is finer and which one is coarser? Are they even comparable?
Tau 2 is finer.
Say it again.
Tau2 is finer than Tau1.
Yes, because among all subsets, certainly there's the empty set in X itself. So this one is finer. So this is Stupa's kind of example, but it comes up sometimes, both of these, the indiscrete topology and the discrete topology. Right, so the claim is that in this quotient example, we're considering the finest topology for which Q is continuous. And let me justify this. So suppose, let tau be the quotient topology. So let's just say what that is. It's U in Y such that the preimage is open in X. And suppose tau prime is some finer topology. Strictly finer topology. If it's strictly finer, there must be some U in here such that U, it doesn't, yeah. In fact, I could just say any other topology. No, it should be strictly finer. So there's some U which is not in tau. But what does it mean for U to be not in tau?
Because the preimage of Q isn't open in X.
Yeah, this means that this is not open. And so by definition, so Q cannot be continuous with respect to this other topology, tau prime. Okay, so there's no finer topology for which Q is continuous, but also if I have any coarser topology which is still comparable, then I claim Q will also be continuous to that, with respect to that. On the other hand, if tau prime is coarser than tau, then U in tau prime implies U is in tau, so the preimage is open. And therefore, Q is continuous with respect to any topology that's coarser than tau, but it has to be comparable. Okay, so that's what I mean as the finest topology for which Q is continuous. And you can prove more about this quotient topology, and we will probably eventually. Yes, go
Can I
ahead.
ask a question? Could there be a case such that if U is topology, such that map Q is continuous, but U and tau are not comparable in these terms?
You're saying there's two topologies which are not exactly comparable.
Yeah. Could there be such a case?
But I don't think so. Because suppose I had some other topology T prime. As soon as it contains some subset which is not in tau, the preimage of that will not be open.
Yeah, thanks. right?
So in some sense, tau, this quotient topology is really the natural one to put when you have a surjective map. Any other topology for which is continuous has to fit inside of this one. Okay. Okay, so we really should do these last two problems from the list. And the question is the following. First question is the following. Can we say anything about the set of interior points? So what to say? What can we say? Of, so there'll be two cases, a everywhere dense subset and a nowhere dense subset. So the definitions of this everywhere dense and nowhere dense were supposed to be in the lectures, but let's remember. Okay, let's call it Z and Z to have it a name. Okay, so right, so it should be non-empty probably. So for all non-empty subsets, open subsets, this is non-empty. Yes? Okay, there'll be an equivalent definition actually. So it's equivalently, the closure is X. I claim that these are equivalent. And nowhere dense means what?
Well, there are two definitions. For example, one of them is there is no interior points in the closure of A.
Okay, so no interior point in the closure, and that's supposed to be equivalent to something else.
The second is for every segment, we can find another segment inside it, which is not intersecting our set.
Okay, let me state it like this. I think it's equivalent, but it will make sense for a general topological space.
In every open set. So.
Yeah. Right, so we say for all U open, maybe I'll have to take it on empty, we'll see in a second. U intersect Z is not dense. Is not dense in U. So I probably want this non-empty. So what are the basic, if X is the real line, what's a dense subspace? Or everywhere dense? I know there's no difference really between everywhere dense and dense. What's the standard example of a dense subset of the real line that's not the whole real line?
All rational points.
Right. Because every interval contains a rational point. And so this condition of it has a non-empty intersection with every non-empty open set is satisfied. So this is dense because every interval contains a rational point. What about this business about the closure? What is the relevant point here? How can we write the closure? It's the intersection of closed sets that contain it, right? We talked about that last time. And those are, I could take the complement of some opens. But these are opens what? These are opens that are disjoint, right? And so if the only open, which is disjoint from U, is the empty one, then we're looking at X minus the empty set, which is all of X. So that's why these two conditions for denseness are equivalent. So is there anything we can say about interior points of a dense subset? Mm-hmm. Right. So I guess what you've just given is for every open set, there's some dense subset of the line whose interior is that open set. That's fine. But also the fact that you could just take the rationals themselves means that there are dense open sets with no interior points. Yes? Okay. So in A, it's kind of, there's not much you can say in general. Everything can happen. What about B? So you gave me a definition. Somebody gave me a definition of nowhere dense in terms of interior points. So let's try to compare these two definitions. I mean, if I take this as the definition, then there's not much to say. It's defined so that they're in terms of non-existence of interior points in the closure. So I think the only thing we could do is compare it to this. So say no interior point in the closure. And consider consider the intersection with an arbitrary open set. Can this be dense? We're going to call this Z sub U. Can this be dense in U?
No, otherwise its closure would have an interior point.
Right, so the closure of this in U would be contained in the, what's supposed to be all of U, and that would be contained in the closure of Z. All right, so let's say closure of ZU will be contained in the closure of Z. And so if this is equal to U, that would imply there exists interior points. But that's not going to happen by assumption. Conversely, suppose this condition that this intersection with U is always non-dense. So if this closure is always strictly contained in U, why does that imply no interior points? So maybe assume we have an interior point. So we're looking at the contrapositive. Then if I look at U intersect Z, its closure will be contained in the closure of Z intersect U, which will be all of U. So that would be a contradiction. Okay, so these two are equivalent. I don't think there's anything more to say about this problem. It's not terribly interesting. Okay, so the last question on the list is the following. Is the union of dense sets dense? And what about the intersection?
The first one is yes, the second one is no.
So let's give explicit examples. Well, let's give an argument for this one and a counterexample for the second one. So suppose, I don't know, Z1 and Z2 are both dense.
No, the closure of their union contains the closure of each one.
Correct. And each of these is both just equal to the whole space. What about a counterexample for the second one? So can we give two dense subsets whose intersection is not dense?
Yes. Rational numbers and rational numbers plus square root of 2.
Intersection?
Rational numbers plus square root of 2.
By plus, you mean union.
No, I mean.
You mean oh, plus, like I see. A translation. So you mean A of B plus root 2, where A of B is in Q. Okay, very good. Right. So what's the intersection of that?
Space.
That's right. Okay, very good. Okay, that's all. That's all that we had on the list, and we did stuff that wasn't on the list too. I hope it was helpful. It seems that they are trying to go slowly and treat very simple low dimensional examples. Maybe they're wise and that's a good thing, and I'm just confusing you with abstractions. I don't know. How do you feel about it?
I like it.
That's okay.
Okay. Okay. Okay. Then till next week, I suppose. Next week we just have one seminar as usual on Wednesday.
Yeah, thank you. Yeah.
Okay. Yep. Goodbye.
Thank you. Goodbye.
Thanks.